a very good morning to everyone. In this class, we will talk about, we'll do a few more examples on how to design state feedback. So in the previous class, we were seeing at what state feedback is. So basically a state feedback is something which means that whenever you're modeling a system, if you know all the state variables or the feedback that you are providing or the feedback sensor that you are giving in your system, wherein the input to the feedback sensors are the state variables. If that kind of a feedback mechanism is present, that is known as a state feedback. Okay. So there can be two kind of cases. So the first case is if you can measure all the state variables in your system. If all the state variables that you have selected for your system, if they are measurable and controllable, if both these two conditions are satisfied, then you can implement a full state feedback. So full state feedback means you will take the feedback from all the individual states. If you have like n number of states in your system or n number of state variables in your system, so then you will have the feedback from all the n state variables and that will consist the whole feedback. So that is known as the full state feedback. So this will give you an ideal condition, but generally when you go for a practical circuit, when we implement any kind of like position control or any other practical control system, in that case what happens is that it becomes difficult to find out or difficult to measure all the state variables that are present in the system. So in that case what we do is that we implement the state feedback by using something which is known as a state observer. Okay, so basically the state observer, what it does is that it estimates the state vector. So in your system you will have a state, the output of the plant will give you there will be a state vector. So since that state vector, let's say if that state vector is x, since that state vector is not known to us, what we will do is that we'll use a separate module or a separate component which is known as a state observer. And the purpose of this state observer is to estimate the value of the state vector, that is x hat. Okay. And finally, using the output of the state observer, we will use it in the feedback loop and we will make the whole system as a closed loop system. Yesterday also we were discussing some examples, and today also let's try to solve a few more examples before moving on to the next topic. So basically, let's say that if you have been given with a transfer function, so this is let us say that this is the open loop or the plant transfer function which is provided. Okay, and the criteria which is given to you is that you have to design a state feedback in such a way that the closed loop, that the eigenvalues of the closed loop system, they lie at the given points. Okay, so what would you do? So the first step would be that since you have been given with a transfer function and finally since you have to design a state feedback, so the first step would be you have to write the corresponding state equation, the state equation corresponding to this transfer function, right? So let's try to do that. So let us say the transfer function which is given to you, that is gs. So this is 10 by s cube plus 3s square plus 2s. Okay, so this is nothing but ys by us, let us say. Okay, so what we can do is that we can write it in this form. Right, this is equivalent to this x1x, x1x gets cancelled out. So we can substitute these, or from these equation we can write that the value of ys by x1s is equals to 10 and x1s by us is equals to 1 by s cube plus 3s square plus 2s. Okay, so from this equation what you can do is that you can simply take the Laplace, you can write the Laplace transform form and then take the Laplace inverse, and then you will end up with the third order differential equation, because the order of this equation is order 3. So you will end up with a third order differential equation, and from the third order differential equation what you will do is that you will select 3 state variables and you will write 3 first order differential equations, so that from the 3 first order differential equations you can write the state equation. Okay, so from this you can write that s cube plus 3s square plus 2s multiplied by x1s will be equals to us. Now if you take the inverse Laplace, so if you take inverse Laplace transform, so you can write that this one will be x1 3, the third order derivative of x1 plus 3 multiplied by second order derivative of x1 plus 2 multiplied by first order derivative, that is equals to u. I'm not writing the t, everything has x1 is a function of t, u is also a function of t. Okay. Similarly for y also you can write that y will be equals to 10 into x1. Okay. So from this equation, let's say that you have selected the state variables. So now let's say the state variables that you have selected are x1, x2 and x3. Okay, so now let's say that x2 is equals to x1 dot, x3 is equals to x2 dot. So x2 dot will be nothing but x1 double dot, and then you will, since you have, and x3 dot will be equals to x1 triple dot. Okay, so here you can write this third order equation in terms of this three first order equations. Okay, so from this equation you will write, so this will be equals to x3 dot plus 3 multiplied by plus 3 multiplied by x3 plus 2 multiplied by x2 is equals to u. This is your one differential equation. The other differential equation will be x1 dot is equals to x2, and the third one will be x2 dot is equals to x3. Right? So you have three differential equations. So you can simply write the state equation. So the corresponding state equation would be x1 dot, x2 dot, x3 dot. So you have 0, so this state equation you can write from the previous the three differential equations that we have already found out. From there you can write. So this will be the state equation, right? So now, so this is your matrix A and this is your matrix B, right? So now let's say that you are designing a feedback, the state feedback that you have designed, that you have to design, that is given by K. Okay, so K will be K1, K2 and K3. So we need to find out the values of K1, K2 and K3. Okay, so and the given thing is that the closed loop, the eigenvalues of the system is of the closed loop system is given. Okay, so what you can do is that in order to find the eigenvalues, what you have to do is that you have to write the characteristic equation of the system, and by solving the characteristic equation you can find the eigenvalues. Okay, so if you write the characteristic equation for the closed loop system, so characteristic equation of the closed loop system. So now your system is, you have, so this is your plant which is given by x dot is equals to ax plus bu. Okay, so you have the feedback K over here, the input here is u, so there is another R, and this is the feedback, right? This is the output y. So this is the closed loop system that you have. Okay, so then the characteristic equation of the closed loop system will be equals to determinant of Si minus A minus Bk equals to 0. Now if you equate this, you will find that the so simply substituting the value of A, B and K. So K we have selected as K1, K2 and K3. So you can write that this equation will come as something like this. So S cube plus 3 plus K3 into S square plus 2 plus K2 into S plus K1 is equals to 0. Okay, so this is the closed loop, this is the characteristic equation of the system. Okay, and the given thing is that the eigenvalues are given. right? The eigenvalues of the closed loop system are given, and as you know, the eigenvalues are nothing but the closed loop poles of the system. So you can write the characteristic equation from the closed loop poles. Okay, so the closed loop poles are given. One is at -2, other one is at -1 plus minus j1, right? So the characteristic equation will look like s plus 2 multiplied by s plus 1 plus j1 into s plus 1 minus j1 is equals to 0. So now if you simplify this equation, and then so you will have a third order equation, and if you compare these two equations, so this is your equation number 1 and this would be your equation number 2. If you compare these two equations, you can find out what would be the values of k1, k2 and k3. And once you know the value of k1, k2 and k3, that is nothing but the state feedback that is provided to you. Okay, in this case, we are considering that all the states or all the state variables that are present in the system, those are available to you for measurement and controlling purpose. Okay, so in that case, we can measure all the state variables separately and we can feed them back using these kind of gains. So the value of k1 will be equals to 4, k2 is also 4 and k will be equals to 1. Okay, so if you can feed back the state variables using these gains. So x1 will be fed back by a gain 4, x2 will be fed back by a gain 4, and similarly x3 will be fed back by a gain of 1. So if you can do like this, then the given condition, that means that the eigenvalues of the closed loop system or the closed loop poles will lie at the positions which are given in your system. Okay. Similarly, if you have, let's say that you have been given with another plant open loop system. Okay, so this is the plant model which is provided to you. So this is x dot, this will be your A, this is your B matrix. Okay, and the desired, so here instead of the desired closed loop poles, what is given is that the desired closed loop transfer function is provided. And in a similar way, you have to find out the state feedback. So again, so you can write that from this equation, you can write that the transfer function of the given system, so this plant model, so transfer function of the given system, if it is ys by us, that is given by c si minus a inverse into b. So this is the equation that we saw in the almost in the first or the second class when we started discussing about state space variable. So from this, so this is your C. So from A, B and C, you can find out what would be the transfer function of the given system. Okay. So similarly, let's say that the feedback sensor that you are designing, that is given by K, and the value of K is K1, K2 and K3. Okay. So what you can do from here is that you can write the closed loop. So this matrix A minus BK, you can write, so A is known to you, B is known to you, using this value, unknown values of K1, K2 and K3, you can write what would be the value of A minus BK. Okay. So now so this A minus BK, this matrix has the unknown variables K1, K2 and K3. So we need to equate this matrix with something which is known to us. Okay, so what we need to do is that we have to find out that what would be the desired value of A minus BK, given that the closed loop transfer function is this. Okay, so from this closed loop transfer function, similarly in the previous example, in a similar way, you can write down what would be the closed loop. So the closed loop state equation, you can write from this from the given transfer function. Okay, and the closed loop state equation will look like x1 dot, x2 dot, x3 dot. It will have a value of something like this. So if you simply take this as y1 y by u, and in the previous example, in a similar way, if you find out what would be the state equation, you will get a value which looks like this. Okay, 0, 1, have x1, x2, x3 plus Okay, and the value of y will be equals to 120. This will be x. I'm just writing the vector. Okay, so this you can also write, you can take 40 out as common and you can say this is 3, this is 1 and 0 into x. Okay, so this is the desired, you can say this is the desired state equation of the closed loop system. Okay, so that means that this is the desired A minus BK matrix. Okay, and so already you have already found out what would be the value of this A minus BK matrix. So A minus BK, this is given by 0 1 0 0 0 1 minus 20 minus K1 minus 6 minus K2 and minus K3. Okay, so this is the A minus BK matrix that you are getting from the state feedback, and this is the actual or the desired one. So what you can do is that you can simply compare these two matrices. You see that the first two rows are same. The only difference is in the third row. So you can compare each element from on the third row, and you will be able to find out what will be the values of K1, K2 and K3. So K1 here is 100. K2 is 56 and K3 is equals to 12. Okay, and here you see that in the gain or in the output equation, we have seen that there is a, if you take 40 as your gain, then the overall the individual path gains, those will be less. So you will be 3, 1 and 0. So in case if you want to have a DC gain of 40, then what you have to do is that you have to take 40 out as common. So if we choose the DC gain to be 40, then we can write that the value of K will be equals to, so this one will become 100 by 40. So this is equals to 2.5. Similarly, this will be 56 by 40. It is 1.4, and this will become 12 by 40. That is equal to 0.3. So you can write that the state feedback that you have designed, that can have smaller gains of this value, but provided that you have an overall DC gain of 42 in the initial stage of the system. Okay, so in that case you can find out that what will be the final state feedback which you need to design in order to get a control system, in order to get this transfer function as the desired closed loop transfer function. Okay, so now we'll move on to another topic, or rather we'll revisit a topic which we had learned earlier. So we'll talk a little bit about the controllers. So controllers, as you have already as we have already discussed earlier in our lectures, that a controller is basically something which is placed in series with a plant, and the main purpose of the controller is that sorry, the main purpose of the controller is that it helps the plant, or it helps the overall system in order to achieve a desired output. Okay, so the three main components of whenever you have a control system. So one will be the plant, obviously. The second would be the feedback mechanism which is provided, or the feedback sensor, and the third one is the controller, which is provided in series with the plant and before the plant. So first you have a controller. So if C is the controller, then you have a plant P, then you have a feedback sensor F, and this will be the input to your system. Okay, so this is plus, this is minus. This is, let's say the input is R and the output is Y or Z something. Okay, so these are the three main components of a control system that you have. Okay, and the main task of the controller is that it provides a control signal. So what it does is that it compares the reference input or the set value which is given. This is R is the reference input, and it compares it with the output. So the output, after being fed back through this some gain over here, so the input to the controller is the error signal between the reference input and the output signal. Okay, or the modified output signal, you can say. And depending on how depending on the requirement of your system, you have to choose your controller in such a way that you can have a proportional controller, you can have an integral controller, you can even have combinations of P, I, P, D, all different kinds of combinations are possible. And depending on what is your system requirement or what is the requirement of the output in the output of your system, you have to design or you have to tune your controller in a specific way. Okay, so now let's just revise about the proportional control that we have already studied. So proportional control, basically it produces the maximum of the corrective effort. So this is the first, you can say this is the first line of control action that is generally provided. Okay, and using a proportional control, what happens is that it improves the sensitivity of the system to different parameter variations. Now there can be two kinds of proportional control. One can be like on-off control kind. So in that case, the control valve or the control element which is present, that will be either fully open or fully closed, depending on the difference between the input and the reference, depending on the output and the reference input. Okay, but the problem here is that since it is fully opening and fully closing, and so that means you can understand that there will be multiple number of switching of the control element. So the moment you have multiple number of switching, so that means it will result in mechanical wear and tear, and as a result that will be the lifetime of the control element that would be reduced. Okay, so in order to cater to that, what you can do is that we can use the concept of something which is known as a proportional band. Okay, so proportional band is basically defined as the percentage change in the input to the controller, the input to the controller being the error signal, which is required to cause 100% change in the output of the actuator. So that means in order to change, in order to provide 0 to 100% change in the output of the actuator, whatever gain of the system is needed, that is known, or whatever percentage change of the input is needed, that is known as the proportional band. And the proportional band, that is related to the proportional gain, that is given by Vp is equals to 100 by gain this much percentage. So that means you can say that if the proportional gain of your system is more, that means the proportional band will be less, and if you have higher proportional band, then the proportional gain of your system is lower. Okay, and smaller proportional gain is obviously, and or rather higher proportional band, that is generally related to better system stability. But the disadvantage of having a very high proportional band is that the response time or the reaction of the output, that response time becomes much slower. Okay. And another important issue with using this proportional control was the problem of proportional error or the offset error. So what is this offset error? So this offset error is something which is a constant difference which is present between the input and the output, which is always present. And so that means that the output of the, if you have a only proportional controller and if you have a set reference of R, so that means using that proportional controller, it is not possible, or the output will never be able to reach the set input. There would always be a difference between the set input as well as the given and the output of your system. So that means that there will be a steady state error which is always integral to the proportional control. So what we can do here is that we can use something which is known as an integral control. Okay, so using integral control, the advantage of using integral control is that it nullifies or it eliminates the steady state error between the output and the set reference. Okay, so that's why this is known as another term of integral control is known as reset control. So what integral control does is that it reduces or it eliminates the steady state error completely. So that means that the accuracy of your system, that accuracy or the steady state accuracy of your system, that improves if you use an integral control. But then again, an integral control means what? Integration is 1 by S, right? So that means you are introducing a pole, an extra pole to your system, and the moment you are introducing an extra pole to your system, the relative stability of the system reduces. So even though this integral control is actually reducing the steady state error or improving the steady state accuracy, it also it comes along with the with reduction in the stability of the closed loop system. So there is a chance that if you don't select the value of this integral action, so the integral gain or the integral time, if you don't select that value properly or appropriately, then the closed loop system might go to instability. Okay. So this is one of the drawbacks of using integral control. So another drawback is that the integral control is generally slower to respond. So proportional control, basically the moment you have there is a change or a deviation or an error signal, immediately proportional action will start providing output. Okay, but in case of the integral action, the response time is much higher. So that means that it is slower in response. So you can say that if you have a larger integral action, then the reaction time will be less. So the reaction or the response time will be less. So it will be very fast. It will give you a faster response, but at the same time, it will reduce the stability of the system. So faster response means there will be a change in the maximum overshoot, and all those things will be more. So in that case, the relative or the system stability of the system stability that reduces when you have an integral control. Then we have another type of control which is known as derivative control. So in case of derivative control, what happens is that derivative control is basically it is dependent on the rate of change of error signal. So it is not dependent on the exact value of the error signal, rather on the change or the slope of change of the error signal. So if you have a constant deviation, so if you have a constant deviation of k, so then you can say that if this dk dt is obviously equals to 0, so that means a derivative of a constant is equals to 0. So you can say that if you have a constant error in your system, then derivative control will not work, because this derivative control, the derivative of the constant is equals to 0, and the output of the controller will be also equals to 0. So it will not generate any control signal. But if your error signal is changing with time, then depending on the rate of change of that error signal, this derivative control can take over. And what it does is that it anticipates the error, and it helps in taking very early corrective action. So early corrective action means action, and that means that it provides support so that the error, it doesn't let the error to become too large. Okay, so the difference between the output and the reference input, so it anticipates that and it immediately starts producing some control signal, so that the difference is suddenly it doesn't become too large for the other control actions to handle it. Okay, and also since using a derivative, so derivative control means you have an s in numerator. So the moment you have an s in numerator, so that means you are introducing a 0 to your system. So introducing a 0 to your system means that the system stability improves. And the improvement of this system stability, that is generally done by increasing the damping of the overall system. So the moment you have a derivative control, so that the main significance of the derivative control is that it produces a control signal depending on the rate of change of the error signal, and it helps in improving the system stability, as well as it increases the damping of your system. That means by increasing the damping of your system, it prevents the system into going into sustained oscillations, or even going into instability where you have unbounded oscillations in your system. So these are some of the, like, whatever we have told right now. So just in a tabular form. So in case of a proportional action, so what we do is that generally when we design a controller, we don't usually change the proportional gate. What we control is that we change the value of this XP, that is the proportional band. So if the proportional band is larger, then the stability is better, but the reaction time is slower. If the proportional band is less, then the stability is worse, but the system becomes fast. System responds faster. Similarly, for integral action, if your integral action is less, so that means that the integral time is more, then the stability improves, but then again the reaction time becomes slower. And if you have larger integral action, then the system responds faster, but at a cost of reduced stability of the overall system. And for D, if you have larger D action, then the stability is worse, then the response will be faster. If you have smaller D action, then also the stability is not really improved, and at the same time the response is slower. So you have to choose the value of this derivative control. It has to be an optimum one. So at the optimum condition, the stability is also improved as well as the reaction time. There is a balance between the stability as well as the reaction time of the control system. So if you write from a mathematical point of view, so proportional action means the output of the proportional. So if this is your controller and this is the input, so input is, let's say, E of t, and the output of your controller is, let's say, U of t. So this is your controller. Okay, so if this is a proportional controller, so you can write that ut will be equals to kp into et. Okay, so kp is basically known as the proportional gain, and proportional gain kp, and that can be written as 1 by xp, where xp is the proportional band. Similarly, for integral action, so the output u will be equals to ki integral of this error signal e dt. For derivative control, you will have the output will be u is equals to kt kd derivative of the error signal et. Now, if you have a controller where you have all the three P, I and D, so if you have a PID control, then the output of the PID control will be nothing but the addition of all these three outputs. So you'll have Kp into E plus Ki integral E dt plus Kd ddt of E. Okay, so basically Kp is the proportional gain, Ki is the derivative gain, and Kd is known as the Ki is the integral gain, and Kd is the derivative gain of the PID controller. Now, if you write the transfer function of this PID controller, you simply take the Laplace transform of this equation, and let's say that GC of S is the transfer function of the PID controller. In that case, you will see that this is equals to Kp into 1 plus this will be 1 by TIS plus TD into S, where Ti is basically known as the integral action time, and Ti is equals to Ki by XP, and TD is the derivative action time, and the value of TD is equals to KD into XP. Okay, so how we got this is that if you have, so similarly if you have this transfer function is given to you, so you can find out what would be the output of the system. Okay, so the output of the system, if this is given by, or the output of the controller, if it is given by YT, so you can simply take the inverse, or from this equation also you can write. So Kp you substitute it by 1 by xp into Et, then Ki, so you substitute Ki again, so you have Kp over here, so 1 by xp, and then you have Ti, and for this one you have Td in the numerator and xp in the denominator. So from this equation you can write that this Ti and Td are basically the integral action time and the derivative action time. So when we are selecting when we are tuning or we are selecting the parameters for a controller, we generally change the value of XP, Ti and Td. So these three are the parameters which so XP, Ti and Td. So these three are the parameters which we usually tune in order to get the desired output. Okay. So now let's try to design an electronic PID controller. Okay, so a PID controller means it has a proportional part, it has a derivative part, and as well as it has an integral part. Okay, so the proportional part would be nothing but a simple amplifier, right? The derivative part, that is, derivative means there is an S in the numerator, so you can represent that as that would be nothing but a high pass filter, and for corresponding to the integral part, that is 1 by S part, that will be nothing but a low pass filter. Okay, so you can simply draw using an op amp, so using two op amps rather, so you can draw that this would be the circuit for designing an electronic PID controller. Okay, so here you have this. So if you write the expression, so if this point, the voltage as this point is E, so E by EIS will be nothing but minus Z2 by Z1. So Z2 you can find out from this one. So Z2 is R2 plus 1 by SC2, right? And Z1 will be R1 parallel to 1 by SC1. Okay, so Z1 and Z2 are given by these expressions. So you can simply write what would be the value of E by EIS. Okay, so this is given by this expression. And if you write the expression for E0 by E, so E0 by E is also, this is also an inverting amplifier. So that means the E0 by E will be equals to minus R4 by R3 will be equals to minus R4 by R3. So overall, if you write E0 by EI, so E0 by EI will be equals to E by EI multiplied by E0 by E. So we just simply multiply these two equations and you will end up with an equation which looks like this. Okay, so this is the transfer function of this electronic PID controller. Okay, and we had already seen that the general transfer function of a PID controller is given by this expression. So what we can do here is that we can simply compare these two equations. So this is the transfer function of the electronic PID controller. Okay, and this is the generic, so this is the general expression, general transfer function you can say. So if you simply you compare these two equations, you will see that Kp is equals to this R4 into R1C1 plus R2C2 divided by R1 R3C2, and then Ti is equals to R1C1 plus R2C2. So similarly you can find out the value of Ki. So Ki is equals to Ti multiplied by Xp, or you can write, so 1 by Xp is nothing but, so this is nothing but 1 by Xp, right? So from that equation you can find out the value of Ki. Similarly, you can find out what would be the value of Td and Kd. Okay, so this is the way of designing a PID controller. So where you can change the values of this R1, C1, R2, C2, R3, C4. So you have 6 different values or parameters to change, and by changing these parameters you can change the overall, you can change the proportional gain of the system, you can change the integration time of the system, you can change the derivative action time of the system. So you have multiple parameters which you can change in order to control these 3 parameters depending on what your actual what your desired output is. Okay, so now how do you choose, like, so now you see that there are like 6 parameters. So obviously if you want to change one parameter and see the effect, then that is one way of doing. You change individual parameters, keep the other parameters constant, and you see what is the effect of the change in those parameters to the system. Okay, so in order to so Ziegler-Nichols, basically they have made a rule, or they have come up with a set of rules for tuning PID controllers. Okay, so there are 2 approaches of tuning a PID controller. This is the general approach, you can say. So in general, these are the methods of tuning which are generally used in order to get a desired response. So what you do is that, let us say that if the plant which you are trying to the plant which you are trying to control, if that the transfer function of that plant is known to you, in that case what will happen is that, so the first approach is you have to tune the PID controllers in such a way that in the case where the plant transfer function is known to you. Okay, so you can say that if you have a purely proportional control, that is this controller is a purely proportional control, then the system will be asymptotically stable in a range of Kp less than Kc. So Kp greater than 0, less than Kc, where Kc is basically the gain of the overall system at which the system becomes marginally stable. That means at the value of Kp is equals to Kc, the system is marginally stable and it has an oscillatory response. So the way of doing this is that, first of all, we need to increase the Kp of the system. We need to increase it from 0 to Kc. So increasing the proportional gain, that means that we have to reduce or decrease the proportional band until the process starts oscillating. So once you have found out that gain, so that critical gain is Kc. Okay, so that means at Kc the system is marginally stable. So after Kc you have to, or near about Kc, you have to do the gain adjustments. You have to be very careful while doing the gain adjustments, because there might be a case that if you adjust it, if you make it slightly higher or little bit higher than Kc, then the system will go to instability. Okay, so here at near about this value of Kc, you have to be very careful while adjusting the gain of the system. Okay, and once you know the value of Kc, you can also find what would be the period of oscillation of the of the sustained oscillation. Okay, so you can find it from the Routh-Hurwitz criteria. Okay, so once you have found out the value of Kc and the corresponding period of oscillation T, so you can, so there is a set of, or there is a rule or set of recommended settings for this value of Kp, Ti and Td. So if you have a P controller, so then you can set the value of Kp as 0.5 of Kc, and that will give you a satisfactory response. So Ti will be infinity, Td will be equals to 0 in case of a proportional controller. When you have a Pi controller, then the value of Kp will be equals to 0.45 Kc, Ti will be equals to 0.83 T, and Td is obviously equals to 0 since it is a Pi controller. In case of a PID controller, the values of Kp is 0.6 Kc, Ti is 0.5 T, and Td is 0.125 T. Okay, so these are the standard or the recommended settings for the values of Kp, Ti, and Td, which are proposed by Ziegler-Nichols, and that is generally these, if you follow these recommended settings, then the output of your system or the system the desired output of your system is generally achieved. And obviously you have the other parameter also. You can always change the value of the feedback depending on whether your system is depending on the specifications of the system that is provided. Okay. So now if you have this, if you take this PID controller with these three parameters into consideration, and if you write the transfer function, so the transfer function, you can simply substitute the value of Kp, Ti and Td. So you will see that this is given by this. This is the transfer function of the PID controller is given by this expression. Okay, so here you see that this controller, this PID controller, it has a pole at origin because of this S, and it has two zeros, double poles or double zeros at S equals to -4 by T. So this is the property of the PID controller. So if you draw the root locus of the overall system, then you can see that after adding this PID controller, it will introduce a pole at the origin and it will introduce two zeros at -4 by T. And so the method for finding out the value of Kc and T, it can be found out using the Routh-Hurwitz criteria. So the first step is that you write the closed loop transfer function of the system under purely proportional control. Okay, and then you formulate the Routh array and you find out what would be the value of this critical gain Kc such that it produces an all zero row. Okay, the moment you have an all zero row, so from that all zero row you can find out the corresponding value of the gain. Okay. And once you know the gain, you can write the auxiliary equation from the previous row, and from the auxiliary equation, if you solve the auxiliary equation, you will find out, or you will get the period of oscillation or the period of the sustained oscillations which are present in your system at the gain, at the critical gain of Kc. And once you know these two values, Kc and T, you can simply use these recommended settings, and depending on what kind of controller you are using, either you will have the values of Kp and Ki and Td. These things will keep on changing. So this is just an example. So you have a unity feedback system. So this GS is given to you, and what you have to do is that you have to find out what would be the controller settings for P, Pi and PID. And once you have found out this the controller settings for P, Pi and PID, then you have to find out if you have a if you give a unit step response or a unit step input to your system, then what would be the output of the, or what would be the output of the closed loop response of the closed loop system for P, for only proportional control, Pi control and PID control. And the second approach for controller tuning is where comes in the case where the plant dynamics is not known. Okay, because most of the times it happens that the plant which you have, obviously it might be it might come up or it might show as a black box to you. So you don't know what is actually happening inside the plant. So all you have been given is that this is the plant, which we don't know what is there inside. You have a controller and you have some feedback. Okay, and you have to find out what would be the final value of the or the desired Okay, so in that case, how would you control? So if you don't know the transfer function of the system, then you can't use the previous method to tune the controllers, because for using the previous method, you need to know the transfer function. You have to write the characteristic equation, and from the characteristic equation, you have to find out the critical gain and oscillation time or period of oscillation. So that process is not possible when the plant dynamics is not known. So what we can do, so can we not tune a controller in that kind of a scenario? Yes, obviously we can. So how we do that is that, so first of all, what we do is that you have the process. So the input to your process is, let's say we provide a unit step input to the open loop plant. So this is the process whose transfer function is not known to us. So we provide a unit step input to this process, and we observe what is the output of the, or we observe what is the transient response of the open loop system. Okay, so if the so in case the plant does not involve any integrator or any dominant complex conjugate poles, the unit step response generally looks like a S-shaped curve. Okay, so if you have if the output or the unit step transient response of the open loop system has an S-shaped curve, then we can use the Ziegler-Nichols tuning recommended settings in order to tune the controller. But in case this kind of an S-shaped unit step transient response is not found, then we cannot use the Ziegler-Nichols method. Then in that case, what you have to do is that you have to use the root locus method, or you have to individually find out the different values of Kp, Ki, Kp, Ti and Td from after drawing the root locus. So that is like the worst case kind of a scenario, you can say. Okay, so in case if your the unit step response looks like an S-shaped curve, so what we do is that from this curve we identify two constants. Okay, so one is the delay time, that is given by L, and the other one is the time constant. Okay, so and this L and T, they are usually measured by drawing a tangent at the inflection point of the S-shaped curve. Okay, so and the inflection point is such that the slope R of this tangent at this inflection point, that is the maximum slope possible for this kind of a curve. So that point is known as the inflection point. So if you draw the tangent at the inflection point, and let's say this tangent, this actually intersects the time axis at some point, and it intersects the value of the line yt is equals to k, where k is you have yt is equals to k line. So from that you can find out, so k is basically the gain of your system. So in that case, the time between, you can find out the value of L and T from these 2 points. Okay, so the time after which this is, so if you similarly if you draw the control valve, the sort of, you can say that if you draw the response of the control valve, or when the control valve is opening and closing, or the control element is opening and closing, so the moment the control valve is open, so the distance between, or the time between the opening of the control valve and the time at which this tangent is crossing the time axis, this is known as L, and from this point to the point at which this tangent is crossing that yt equals to k line, this is known as the time constant. Okay, so once you can find out the values of t and L, so this kind of an S-shaped response, that can be, so the transfer function, if you approximate the system or the plant which is given to you as a first order system with transportation lag, that means the transfer function of the given plant will look like something like this: k into e to the power minus ls divided by ts plus 1. And if you draw the unit step response for this system, it will look like an S-shaped curve. Okay, and from this S-shaped curve you can find out the value of L and T. And once you know the value of L and T, you can use these recommended settings for which are provided by Ziegler-Nichols rules, and you can find out, or you can tune the overall controller of your system. But then there is a trick here also. So here, if the value of t is relatively larger compared to L, that is the time constant is relatively larger compared to the delay time, in that case the process can be easily controlled using a simple controller, and there is using only these kind of rules which are provided. But in case if you have a system where the delay time L is very large and it is almost comparable to the time constant, in that case it becomes difficult to control or difficult to tune the controller. In that case, if we use only these kind of parameters, then this is not sufficient to provide a proper tuning of the controller. Okay, so in that case what we need to do is that we have to go for we have to use the root locus technique. So we have to draw, so given the transfer function of your system, you have to draw the root locus for if you have only P controller, then you have to find out what would be the value of this proportional gain. Then again you have to modify that proportional gain. If you include the value of P and I, then again your root locus will definitely change, and then again from that root locus you have to find out what would be the recommended settings for the proportional and for Kp and Ti in that case. So that in that case, in that kind of a scenario, what happens is that tuning of the PID controller, that becomes a tedious process. But in general, for simpler control systems, the Ziegler-Nichols method, this is an ideal method, you can say, in order to select the controller parameters, or in order to tune the controller parameters. The Ziegler-Nichols method, this is an ideal way of, or a more or less an ideal way of selecting or tuning the controller parameters. Okay, so I'll stop here right now. Do you have any doubts? Any doubts till now? Okay, so it seems that you don't have any doubts, so I'm assuming that you have understood everything. So as I have already mentioned in the group that the quiz will be held on Tuesday from 5:30, and we'll also have a class on Tuesday from 2:30 to 3:30, and then in the evening you will have your quiz. Okay, so all the best for the quiz, and that's all from my side today. Thank you, everyone.